Okay, I want to welcome you to my lecture today. Of course, today I'm going to be walking you through another exciting topic in statistics. Of course, I told you the other time, statistics is like a story that goes on and on and on. Today, the focus is going to be on ANOVA contrast and comparisons. Of course, this is going to be taken from chapter 4 and 5 of the reading, of the recommended textbook. Okay, so we got a lot to talk about today. In the outline, I'm going to start with checking ANOVA assumptions. Of course, these ANOVA assumptions is also included in the slide for Wednesday. So I decided to add it to what we're going to do today. Then we're going to focus on linear contrast, then the multiple comparison. Of course, the multiple comparison, I think that objective will be achieved on Monday. So which means what we want to focus on today is just going to be the first two. Now, before now, I actually introduce you to analysis of variance, particularly one-way analysis of variance, which is actually a statistical technique for comparing means in more than two populations. And we use one-way, it is called one-way analysis of variance because we are only focusing on one factor. And of course, the factor is categorical. It has levels. That's why it is a factor. Before you can use analysis of variance, the independent variable has to be categorical. So the moment you have one independent variable, okay, then we call that one-way analysis of variance. In the previous class, I think I walk you through how to, set up the ANOVA table and how you can partition the sources of variation into various components where we focus on error when we focus on variability between groups and the variability within group. I think I walk you through that. But let me tell you this, anytime we want to make attempt to use statistical model to capture reality, every statistical model has assumptions, and we need to be able to investigate these assumptions, because if we don't do that, whatever we're going to achieve with that model, okay, it's not going to be valid. A model is as good as assumptions put into the model. And that is why, just like what I used to say, it is not as if our models are failing us, but we are the one that we're not doing the right thing. When you don't check, when you ignore assumptions, then your model is going to mislead. Does that make sense? And ANOVA is not left out of statistical model that requires assumptions. Now, when we're talking about assumptions of analysis of variance, as you can see, like what I'm displaying now, number one is independence, observations, and independent groups. The groups that you want to compare have to be independent. That's what we mean. And not only groups being independent, observations have to be independent as well. That is required. Okay. Now the second assumption is constant variances across the various groups. I'm actually going to call the constant variances across the various groups. We call that homoscedasticity. That's what we call homoscedasticity. This is required. This is assuming that the group that we're comparing has constant variance. Okay, we need to investigate that. That may be true or not. Okay, the only way to tell is where we investigate that. We have a test, to investigate whether assumptions hold or not. Now, the third assumption is that the data set in each group has to be chosen from normal distribution, the normal population. Okay, that is required. And the assumption, when you take a look at these three assumptions, we can actually, put it together mathematically to look like what you see now. EIJ, error is identically, the IID means identically and independently distributed, okay, with mean of 0 and the variance sigma square. Okay, the mean of 0, that means the mean of the error has to be equal to 0. Don't forget, what is the error? What am I talking? What error actually mean? Unexplained variation. Your model does not have, there's no any model anywhere in the world that can actually explain 100% variation in the response. There's always going to be unexplained. Okay, so what we're trying to say now, what we're telling the world, the error must follow normal distribution with a mean of 0 with a variance sigma square. Of course, the error that we're talking about, we can actually predict that. If I want to estimate error, okay, if I want to estimate error, it's going to be called residual. Okay, estimated, estimates of error, okay, is called residual. Okay, we are this is error. Okay, if this guy represent error, then the residual is going to be this guy cap. Anytime you see a cap, that's an estimate. Okay, and what you see now, the difference between the observed value and the expected value, is small. That is exactly what you're saying, which we call the error. Okay, now I told you the other time, every model has assumption. Analysis of variance, ANOVA model is not an exception. It also has assumption. Now I just, I'll tell you now, I just explained that, we have assumptions of normality, assumptions of independence, assumptions of normality. How do we test that? Okay, now if you actually want to investigate whether your residual, and let me tell you this. Every assumption is statistical model centered on error. And what is the estimate of error? Residual. When assumption hold, residual behaves well. We want our residual to behave well. The only way residual can behave well is when assumption hold. Now, if I want to check for normality, I can make use of histograms, box plots, QQ plots, okay, to actually investigate normality, whether the normality assumption hold. If I want to test whether the constant variance assumption hold, I'm going to make use of residual plots, okay. In addition to residual plots, we can make use of Shapiro wiki test of normality. Shapiro, in R, we call it Shapiro.test. Okay, the Shapiro.test is a test of normality. Test of normality. The test of normality of residual. Okay, in addition to, using using box plot, histogram, we can also use a Shapiro or wiki test of normality. Okay, so these are the assumptions, and these assumptions, they are very, very crucial. Okay, I think I just explained that. But about the independent groups, there's no special test. That depends on the way you collect your data. When you are collecting data, you need to be guided Okay, if you are conducting survey, you got to make sure that participant that you select into your survey, you choose them using the principle of randomization. Okay, with that, independent assumption is basically going to hold. And that was why I said the group ought to be independent by design or randomization. What do I mean by randomization? The way you select participants into your sample, you basically need to use the principle of randomization. What do I mean by that? Like for instance, if you are, you want to partition them into groups, maybe you want to test with the quality of groups. Okay, every groups every group must have equal chance of receiving any participant. That's what we mean. Okay, now for the constant variance, of course, in addition to using residual plot, we have several tests, statistical tests that we can actually conduct to test if the assumptions of constant variance hold. I remember Wesh. I remember Bruce Pagan. Okay, there's another test called Bruce Pagan. No, the Bruce Pagan test, the Wesh test, and so on like that. We got different kind of tests, that we can actually use to test whether there's a constant variance or not. Of course, as time goes on, I'm actually going to unfold that in this class. Okay, normality. I just talked about normality. Okay, and let me tell you this: ANOVA is a fairly robust to moderate departure of normality. When when the assumptions of normality is violated, we can still use ANOVA, but that is if the amount of the violation is not severe. If it is moderate, there's no problem. But if it is severe, of course, we cannot use ANOVA anymore. Then we need to actually resort to non-parametric procedure of seeking redress. The non-parametric is going to be Kruskal-Wallis. Okay, or if you don't want to do Kruskal-Wallis, you can perform a randomization test. Oh my God, you remember when we're dealing with the one population, we actually consider randomization test. We can also use randomization test when we are focusing on more than two populations. We're always going to have a way out, okay, like I said. Okay, and we can do transformation. For instance, if you want to still use ANOVA, if you don't want to try non-parametric method like Kruskal-Wallis, if you don't want to perform a randomization test, if you still want to seek redress, okay, in a parametric framework, you can actually transform your model. And that is where we're basically going to consider Boss-Cost transformation. Okay, I remember when I was doing my PhD that I presented in 2016, I was trying to work on, how can we actually seek redress, in the parametric framework when the assumptions underlying the use of analysis of variance fail. Because why I was able to show the world that Kruskal-Wallis could be misleading. Randomization tests could be misleading if there's a serious violation due to outlier, and of course I seek redress in the parametric framework. The only thing the penalty I pay is actually mathematical complexity, because I have to expand the F test. Okay. Now, relaxing assumptions, as I recall, the null hypothesis states mu is the same for all group, but does not mention sigma squared. Don't forget, mu the same. When you look at the non-hypothesis in analysis of variance, it only focuses on mean. It does not focus on variance because it's assuming that variance are the same. That's an assumption that may not be true until you conduct a test. But let me tell you this. According to central limit theorem, when the sample size that you choose, in each group for each group is at least 30, then the data are relatively, normally distributed. But let me tell you, in most of the time, we may not have at least 30 for each group. And that is the reason why we may have an issue, we may have a problem with this. Okay, so there's always going to be a way out whenever there's a problem. I just want you to know that. Now, what I'm presenting to you now is just the code. Okay, the code, if you want to investigate constant variance, normality, my TA is going to walk you through this in lab. Don't forget, we're working on an example that we started on Monday that has to do with effects of sandwiches on attracting ants. We consider 3 types of sandwiches. Of course, this is a model of this is an R code where if you want to, this R code is going to generate residual plots, the QQ plots, and take a look at this guy now. This is if I want to check for constant variance absorption, and this is a normal QQ plot for normality. Of course, I expect most of the point to be on the diagonal straight line, okay, and I expect that particular diagonal line to start from the origin, for us not to have a violation of normality. And don't also forget, if all else fails, remember, you can also create a randomization test. I think I just told you now. Just like what you did your time. Now, what is the take-home lesson here? Of course, ANOVA can be used to compare means among populations. And of course, we use the idea of sum of square, that use variability measure. Variability measure, don't forget, we consider variability between groups, variability within group, and don't forget the F-test that we actually use is a ratio of between group, between variation divided by within variation, and of course the p-value of the test. We basically use that to figure out the p-value of the test. Okay, now today we want to go into contrast. Now let me prepare your mind. We're dealing with the analysis of variance. And in analysis of variance, we basically want to test whether the means of more than 2 groups are the same or not. That's what we want to do. What do I mean by contrast? We got the contrast is just trying to tell us how we can compare the means of 2 or more levels of an independent variable. I'm going to write it down. Okay, that's what the contrast, by contrast, we actually, to compare the means, to compare the mean values, okay, of 2 or more levels of an independent variable. Okay, that's what we mean by contrast. Okay, we're focusing on one independent variable. Don't forget, we're focusing on one-way analysis of variance. In one-way analysis of variance, you're actually going to have one independent variable. The independent variable has levels. Don't forget, it's categorical, right? Now, how do we compare 2 or more levels of an independent, variable? Let me tell you, we got 2 types of contrast. Okay, we have what we call a planned contrast. The planned contrast is what we want to do today, and we have a post hoc contrast. Okay, the one we want to focus on today is the planned contrast. Let me tell you the meaning of the planned contrast before you go into experiments, before you conduct ANOVA. Maybe you have certain hypotheses in mind that you actually want to test. That's what we call planned contrast. Before you go into research at all, I'm going to give you an example now. When we want to talk about whether intervention work, during the COVID. Of course, during the COVID, no mitigation. This is going to be like control. Okay, social distancing. Okay, wearing face masks, mask. Then vaccination. Take a look at what I have here. These are like, I got 4 levels here. No mitigation. No mitigation actually means you are not doing social distancing, you don't wear face masks, you're not vaccinated. That is no mitigation. Then the other 3, of course, is with mitigation. These 3: social distancing, somebody that is doing social distancing only, those who are wearing face masks only, and those who get vaccinated. Okay, what if I want to compare the infection rates? Let's say the response variable is infection rates. Okay, I want to compare infection rate of these 4 groups before going into experiment, before conducting analysis of variance. Maybe I basically want to, maybe I have it in mind that this guy, okay, maybe I have it in mind that vaccination, okay, the infection rate, for those in the vaccinated group will be less than all this together, all of that together. That's a planned contrast. Okay, I was able to have the planned contrast based on experience, based on theory, even before going into the research. That's a planned contrast. Or, I may also want to compare, this guy with the combination of the other 3. That's a planned contrast. Or I may want to compare this guy with any of that. That's a planned contrast. But let me tell you this. If I want to talk about post hoc contrast, when do we use post hoc contrast? Oh my God, post, which means you've already conducted analysis of variance. You have a result, and you've rejected the non-hypothesis. And that shows there's a difference. There's a statistical significant difference. And you basically want to know where the difference lies. And you conduct a pairwise comparison. That is what we mean by post hoc contrast. Any question on the difference between planned contrast and post hoc contrast? Any question now? The first one, you've not conducted ANOVA at all. But the next guy, look at that, post. You've already conducted analysis of variance tests and you've rejected the non-hypothesis. Let me tell you this, the only condition under which you will go for post hoc test is when the non-hypothesis is rejected. If it is not, you don't need it. Because the analysis of variance will not tell you where the difference lies, even if there's a difference. But what tells you where the difference lies is the post hoc test, where you're actually going to compare the level of the treatment, on head-to-head basis. Does that make sense? Before I go into this, I'm going to give you another example from politics. Let me tell you, I understand my statistics very well because I relate. I give my own example. Make sure you always give your own example. I'm going to give you another example now. I just give you an example from COVID. I'm actually going to give you example, looking at the way United States legislators actually vote in Congress. Now I want to talk about tobacco votes. Okay, in the United States, we got 4 regions, right? You got the South, okay, you have the Northeast, you have the West, and you have the Midwest. Okay, these are regions in the United States. The Congress, the legislators in the United States actually come from these 4 regions. Now, if I have these 4 regions and I want to do a planned contrast, okay, maybe I actually want to compare the voting, the tobacco voting rates among legislators in this 4 region. Okay, now maybe what I have in mind is that the legislator from the South normally vote more when it comes to tobacco industry than any other state, I mean, any other region in the United States. That is a planned contrast. Or maybe I'm trying to say, okay, the North East, okay, maybe the legislator from the Northeast vote less when it comes to tobacco vote compared to the South. Okay, now that's a planned contrast. Okay, now I want to take us back to the example that we did the other time on sandwiches. Now take a look at what you're seeing on the board. What you're seeing on the board now, what of, when you look at the sandwiches, the 4 sandwiches has to do with meat. But the other 2, they are non-meat. If you remember the example that we were treating in this class on 3 types of sandwiches, okay, we have A, B, C. The first one, the first sandwiches is meat. The second one is non-meat. And I want to compare the 2. 1 level here against 2 levels. Look at that, 1 level against 2 levels. That is what you see on the board. If I want to do that, I need to assign a weight. I'm comparing this guy with this guy. This guy is going to be 1. This guy is basically going to be minus half in such a way that when I add them up, that should give me 0. So why is it 1/2, 1/2? Because I'm comparing this guy with 2. If I'm comparing 1 with 3, then the other, each of the 3 is going to be 1/3, 1/3, 1/3, negative, 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 and 1. Does that make sense? Now take a look at what is on the board. That's what we're doing. Now, how does it work? I need you to pay attention to this. This is on the exam. If you look at it, midterm 1, practice question, of course, there's a question from this area. Now, if I want to construct a linear contrast now, it's basically going to be a linear combination of weights and mean. That is what you're seeing now in such a way. The sum of the weights have to be equal to 0. This is weight. Sum of that. When you add this to that has to be equal to 0. That's what you're seeing now. Now, if I have groups, what determines the number of contrasts I'm actually going to derive depends on the numbers of groups. If I have 3 groups, the maximum number of contrasts that can be derived is going to be 3 minus 1. The numbers of groups minus 1. If I got 3 groups, I can only derive 2 contrasts. Now, if you take a look at what I'm showing you now on the board, if G equal to 4, I have 4 groups, right? And I only want to compare 1 level with another level. If it is a 1 with another level where I got 4 levels, the other level will be 0, 0. Then the level you are comparing will be 1 and minus 1. Does that make sense? In terms of weights. Now, oh my God, take a look at number 2. Now, what do you think? 1 minus 1/3 minus 1/3 minus 1/3. It means I got 4 levels and I'm comparing 1 level with the other 3. Does that make sense? Okay. And we can also have, when you're talking about planned contrast, we have a linear contrast, we have a polynomial contrast. Okay. So the polynomial contrast, if you look at number 3 here, particularly when I'm talking about those, okay, we're actually going to use -3, -1, 1, 3. Let me tell you, when we use a polynomial contrast, let us assume that I, as a researcher, maybe a researcher predicts that his clients, okay, clients have, average, motivation to attend therapy, okay, in the course of the treatment. Maybe you realize that this particular client, the motivation to attend therapy, initially it decreased. then increase, and later decrease. In this kind of situation, you're going to use a polynomial contrast. It's not going to be a linear contrast. Number 3 that I'm showing you now, that you have -3, -1, 1, 3, is an example for polynomial contrast, where you notice something decrease, later it increase, then it decrease again, continue to go that way. Then that's not going to be a linear contrast. That's going to be a polynomial contrast. Now, take a look at the formula. If you want to develop a contrast, we need a linear combination. That's what I'm showing. The L is a linear combination of the weights and the mu. Then we need the variance associated with the linear contrast. Why do we need the variance? Because we basically need standard error. Don't forget, when you want to conduct statistical inference, whether you want to construct a confidence interval or you want to test hypothesis, you need standard error. And that is the reason why. So what I'm trying to display to you now, the formula on the board, that is the standard error of the linear contrast. Okay, now let us go back to the example on the sandwiches when we're trying to compare the degree of attractiveness of sandwiches to ants. This is the code. We have a data set on sandwich ants, and of course, this is an ANOVA table, generated. But when you take a look at what I'm showing now, this is a linear regression way. You remember on Wednesday, I walk you through ANOVA for regression. If you can see the code on the board, this is a linear regression. The linear regression also perform the job, okay, that we do in analysis of variance. As you can see, we got 3 levels, right? It is only 2 that will be displayed. The other one is intercepts. Okay, now you can say 49.25. The 49.25 that I show you now, that is the mean of the first group of sandwiches. But when you look at the second one that you have, -15.25, that is the difference between the first group and the second group. Okay, that's going to be the difference between the first group and the second group. And the third one is different between the third group and the fourth group. Okay, and they are all significant. But that is not where I'm going. Where I'm going is this. When you have 3 sandwiches, we now want to develop a contrast. Let's say, for instance, we want to test, is there a significant difference between pickles and peanuts? That means in my linear contrast, I'm looking at the difference between mu1 and mu2. That's why you see mu1 minus mu2. Then what is going to be the L? Don't forget, the L is going to be the linear combination of the mean and the weights. The weight of the first group is going to be 1, and the weight of the second group is going to be -1. Then we're going to add them all. Now, after adding them all, that's why you see a negative. Okay, don't forget, let me take you back. You're going to see the formula. Okay, look at head. The head that you see, that is a linear contrast. The head is just L equal W1, mu1, W2, mu2. When you're comparing, mu1 minus mu2, the weight here is going to be 1, and the weight here is going to be -1. Did you see that? And that was why plus times negative. That was why here now you have a negative. Now the estimate of the contrast is 15.25. Then you're going to proceed to find the standard error associated with the contrast. Now, what formula am I using? This is the formula. Take a look at that. Sigma cap, square root, the summation, W high squared divided by N1, which means I'm actually going to have the square of the weight of the first group divided by the number of sample in that group, plus I'm going to go that way. That's what led to 5.885. Now, after having that, now I'm going to tell you what to do next, but here I'm just showing you how to get the lean estimate of the contrast and its standard error when we are comparing the first group and the second group. If you are comparing the second group and the third group, it's still going to be the same way, except that you're using different means now. Take a look at that. But what do you see? Oh my God, the standard error is basically going to be the same. I need somebody to ask me a question that you have not asked me. Where did I get 138.7 from? Let's go back to the formula. You see sigma cap, right? Oh my God. In the analysis of variance table, that sigma cap, if I want to get a sigma cap, that is the square root of the mean square error. Sigma cap, the square root of the mean square error. You remember on Monday when I was trying to show you ANOVA table, right? The sum of we have a mean square error, mean square within, which is going to be the sum of square within divided by the degree of freedom. Okay, so you're going to get that sigma cap from the table. Okay, now we've compared the first and the second group. We've not conducted hypothesis. We've not constructed confidence interval. The only thing we have done now, we estimate the linear contrast and the standard error. We do the same thing for second and the third group. Oh my God, what are we doing here now? We are actually comparing a sandwich that has meat with the one without meat. We realize the first sandwich has meat. The second and the third, they don't have meat. It's more or less like comparing meat with no meat. Don't forget, when you're doing that, the weight, okay, it's basically going to be 1 minus half minus half. Because you're comparing one with the other two. And that's why you're seeing that the linear contrast is going to be that, mu1 minus that. Then you compute your linear contrast estimate. You get the standard error associated with that. Is there anyone who doesn't understand that? We're still using the same, the mean square error, the square root of the mean square error that you got from the ANOVA table. Oh my God. Now that we've obtained our standard error and we've obtained the estimate of the linear contrast, now we are set to conduct statistical inference. How can we conduct statistical inference? Oh my God, what kind of statistical inference do I need? Oh, I want to construct a confidence interval. If I want to construct a confidence interval, of course, you know what we need. It's going to be the estimate of the contrast plus or minus the quantifier, which is the t, right? Then the standard error of that. You now see the reason now why you need the estimate of the contrast and why you need the standard error. Now, in the end, you're going to use that now. You know, I told you the other time that sigma is the square root of MSE. You can see in the formula now, the MSE, you're actually going to get that from the ANOVA table, right? Now, when you take a look at the example 3 that we just did, the moment you plug in those values, oh my God, I have the range now from 6.2510 to 27.46030. What are you comparing? You're comparing meat with non-meat. When you are comparing meat with non-meat, the confidence interval do the job of hypothesis testing. There is no zero in this interval. Is there any zero? When you are from positive to positive, what does that mean? If there's no zero, that actually means there is a significant difference. If it is from negative to positive, then it means there's no significant difference. The confidence level also do the job of hypothesis testing. Okay. Now we've talked about confidence level. I can also talk about testing hypothesis about it. Using the conventional statistical theory, that's going to be head cap. Don't forget, that is the estimate of the linear contrast minus a data. Oh my God, that data will be an hypothesized value. Don't forget, if it is an hypothesized value, if you're looking at the difference between something, automatically it's going to be 0. Then divided by the standard error that you've already found. Oh my God, look at that. Put your L, estimate of L divided by standard error, you get 3.3053. The moment you do that, you can get your p-value. Oh, the p-value is 0.003. What am I saying now? Is 0.003 is less than 0.5. Because of that, you are rejecting the non-hypothesis. Look at that. We are taking the same decision. When I use the confidence interval the other time, I told you when the confidence interval is from positive to positive, that is significance because it does not include zero. But if it is from negative to negative, it is also significant. But if it is from negative to positive, that includes zero. And my conclusion is basically going to be no significant difference. Now, if you take a look at the confidence interval now, with the hypothesis testing that we just conducted, they agree. Okay. Now, I want to talk about orthogonality, orthogonal contrast. Let me tell you this. The number of contrasts you're basically going to construct depend on the numbers of groups you are comparing. If I got 3 groups, the maximum number of contrasts is going to be 2. If I have 4 groups, the maximum of contrast is going to be 3. But we need our contrast to be orthogonal. What is the meaning of orthogonality? Then it means we expect them to be independent. If contrasts are orthogonal, it means they are independent. And don't forget, analysis of variance requires independence assumption. The contrast need to be orthogonal. And how am I going to know? Let's, for instance, look at this example I'm displaying now. I got 3 contrasts, W1, W2, W3. And I want to investigate for orthogonality. I can look at 2 at a time. Look at W1 and W2. What am I going to do in the W1, W2? Multiply elements in the same position. 1 times 1 plus this, this times this is going to be 0. This times this is going to be 0. 1 times 1 is going to be 1. Because I got 1, if I don't get 0, that is not orthogonal. What is orthogonal is when I get 0. And if it is not orthogonal, then it means, when you try and investigate that, you may mislead because orthogonality it requires, it implies independence. What about W1 and W3? What about W2 and W3? How are you going to investigate for orthogonality? Take a look at that. 1 times minus 1 is minus 1, right? 0 times minus 1 is 0, right? Minus 1 times 2 is minus 2, right? So you can investigate orthogonality for that one as well. Just like the same way you investigate orthogonality here. What about W2, W3? Is there anyone in this class who doesn't understand how to investigate orthogonality? Is there anyone? For it to be orthogonal, when you multiply the element in the corresponding position and you add them up, they must give 0 for them to be orthogonal. Okay. Of course, the moment they are orthogonal, then I'll start doing whatever I want to do. Now, if W1 and W3, W1, W3 are orthogonal, how? How are they orthogonal? 1 times minus 1. Okay, I'm going to write something now so that you basically going to see. They said W1 and W3 are orthogonal. W1 is 1 minus 1, 0. W3 is minus 1, minus 1, 2. Okay, multiply this 0, multiply this 1, multiply this minus 1, add them up, 0. It's true. Does that make sense? That is how to investigate orthogonality, and orthogonality implies independence. Okay, then you can go ahead and get your standard error, just like the way we always do. Okay, now let me tell you this. If you take a look at the example that I'm showing you now, W1 and W3, you get that. Okay, I didn't forget about that. I'm gonna go to the next one. Okay, take a look at this guy. W1 and W3 are not orthogonal. Okay, the only unique set of, they are not orthogonal because they don't give 0. Okay, now let us compute this now. Based on W2, 1, 0, minus 1, you know the meaning? 1, 0, minus 1. It means I'm comparing the first sandwich with the third one. The second one is having 0. It means I'm not interested in the second one, right? Now, what you're seeing on the board now is the sum of square associated with that. Okay, that's what you're seeing on the board now. 1369.00 is just basically talking about the sum of square. If I want to consider the W4, where I got minus 1, 2, minus 1, you know what I'm doing? Minus 1, 2, minus 1. Oh, I'm comparing the combination of the first and the third group with the second group. Okay, and I compute that, the sum of square is basically going to be that. And when I add up the sum of square, that should automatically give me the same sum of square between that I have in the ANOVA table. Why am I considering 2 sum of square? Why am I considering 2 orthogonal? Because there are 3 groups. When you have 3 groups, the maximum number of contrasts you basically going to consider will be 2. It's going to be the numbers of groups minus 1. This is, I'm reminding you now, this is ANOVA table, right? That I showed you before. Now, before I go today, polynomial contrast. All what I've been explaining is just linear 1. Linear 1 is just to say linear relationship exists. At times, it may be a polynomial. And when I say polynomial, it could be quadratic, it could be cubic, it could be quartic, and so on like that. But what I suggest to you now, when you have 3 groups and we're dealing with linear, where basically normally you minus 1, 0, 1, when you're comparing 2 levels at a time. If you're comparing 2 levels at a time, you want to talk about quadratic, which is a polynomial, the weight is going to be 1 minus 2, 1. If my group equal to 4, and I want to compare linear, okay, the weight is going to be minus 3, minus 1, 1, 3. If I want to do quadratic, okay, just make use of that. Lastly, today, when do we use linear contrast versus linear regression? And I said, the linear contrasts are used when that is from design experiment. What do I mean by design experiments? When you randomize, that's a design experiment. That is not an observational study. Okay, but we only use regression analysis for observational study. And that is why experimental study has more statistical power than observational study. Because in experimental study, you randomize. But in observational study, you don't randomize. Okay? Oh my God. What we're going to do next is going to be multiple comparison. That multiple comparison is what we call post-hoc test, which is different from what we did today.